Questions from last time? All right, so we're sort of continuing this expansion into the territory we're in now. I think should be familiar because we're doing sort of the same topics, only we're not necessarily restricting ourselves to Rn. We could perhaps consider more general vector spaces, like remember the polynomials we talked about. And I'll show you another couple today. But we're going to talk about today linear independence and bases in this more general setting. So this is probably a good review here. Now here, in this more general situation, the definition of linear independence, we have to really kind of go to the old school original. So let me ask you this. This is what I mean. Somebody tell me what it means for vectors to be linearly independent. How many of you want to say, put them in a matrix, and if every column is a pivot column, right? I want to say that too, right? You can't say that in general, because in general, you might not be able to write things as a matrix. Yes, you can for finite dimensional spaces and stuff we have, but when I'm talking about polynomials, remember the P2 that we talked about last time? The basis was 1, x, and x squared. There aren't any matrices there. Yes?
No vector can be written as a linear combination of it.
Okay, that works. No vector in the set can be written as a linear combination. That one actually works more generally. Yeah.
Yep. To get back to the origin graphically, you can only multiply by factors of 0 by linear combinations of 0.
I'm going to make that a little bit more precise. That's essentially it. The problem is graphically, though, is what if I give you a vector space generated by one sine x and cosine x? Right? What does it mean for those three functions to be linearly independent? So that can run you into a little bit of trouble. Although it's a very good visual thing if you're thinking about Euclidean space. Okay, so this is a definition you've seen before, but now maybe a little more appreciation for it. A set of vectors, let's say V1, V2, Vk in some vector space V is linearly independent this, I think, is what you were saying, Paul, if whenever a linear combination of these vectors is 0, means that all C1, C2, C, what do we call this Cn instead of Cn? What is it called? So the only solution to this linear combination of vectors being 0, you have to take all the constants to be 0. All right. Now we've seen some, so for example, let's just go kind of to an old school. These vectors are linearly independent because if you have C1, 1, C2, 1 minus 1, and suppose it's 0, 0, this forces C1 and C2 both be 0. And let me show you that in action. What's the top coordinate of this vector here? C2. I agree. And how about the bottom? C1 minus C2. So you get two equations, don't you? You have that C1 equals C2 must be 0. C1 minus C2 equals 0. You add these things up, and then you get C1 is 0. And once C1 is 0, and C2 is 0 as well. Right? And so you are forced. So this is what it means to be linearly independent. Yes?
Does that mean it only has a trivial solution?
That's right. You can think of it this way. If you count the trivial solution to be all the C's after 0. What is linearly dependent? Not linearly independent, but I can do better than that. Linearly dependent. So let me give you a theorem. A set of vectors linearly dependent if right, if it contains 0, and it's going to run one on instead, or if one of the vectors is a linear combination of the others. Okay. This is the one that you all like to. So let me kind of clarify this. If you have only one vector, right, and it's not the 0 vector, as long as it's not the 0 vector, that's a linear set. It's only one because it's not a linear combination of the others. If you have a larger set, if it contains a 0 vector, it's automatically linear dependent. And if it doesn't, but one of the vectors is a linear combination of the others, well, it's a linearly dependent set. So, for example, we do a couple of examples of this element. Here, we'll let V equal the set from okay, I've got this big vector space. And they probably didn't talk to you like this in calculus, but when you look at remember how important continuous functions were in calculus, right? You talked about them forever and ever. All continuous functions could be integrated, et cetera, et cetera. They probably didn't say this, but continuous functions form a vector space. But they probably did tell you this sort of offhandedly. What happens if you add 2 continuous functions? What do you get? What's the negative of a continuous function? It's also continuous, right? What happens if you take a continuous function and multiply by a number? Still continuous, right? This is vector space. By the way, this is a huge vector space, much bigger than a line. Right? Let me look at some subspaces. Let S span 1x squared. I claim that these 3 elements here are linearly independent elements in here. Right? Let me prove it. Suppose C1 times 1 plus C2 times x plus C3 times x squared is equal to the 0 vector. What is the 0 vector in the space of continuous functions? It's just a 0 function. Y equals 0. There it is. That's the function you can add to any other function and it leaves it alone. Everybody okay with it? Would everybody agree that this is a polynomial of degree 2 or less? For this to be 0 for every value of x, all these have to be 0. Everybody agree? So this is a linearly independent set. If you're not comfortable with that, let me do this. Suppose I had this equation. Well, check this out. Let's plug in 0. Now put the C1 and 0. Everybody agree? Because when I plug in 0 here, what do I get? I get C1. When I plug in 0 here, I get C1. So C1 is C1. Everybody agree with me? So now I have the equation C2x plus C3x squared is equal to 0. Plug in 1, because this has to hold for every value of x. This function here on the left has to be 0, no matter what you plug in for x. So let's plug in 1 and see what we get. And let's plug in -1. And I get minus C2. That's C3. And didn't we just have these two equations? Almost, right? So it's also true that so this is a linearly independent set. Here's another set. How about this? This one's a linear set. Would everybody agree that 1, sine x and cosine x are all continuous functions? Why is this linear? So for every significant value of x, this thing has to be 0, right? Certainly this works at C1, C2, and C3 at 0, right? It's maybe a little bit less obvious, but doesn't it seem like it should be the case that condition should be forced, right? That is to say, if any of those numbers are not 0, this can't always be 0, right? Let's prove it. Let's plug in by the way, if anybody sees something good, I can plug in. Yes, yeah. 0 is good. Yeah. Plug in 0. C1 plus C3 is 0. If I agree with it. If I plug in 0 for x, that's what you get. What else might be something good to plug in? I'd rather not. Right. What was good about plugging in? What was good about plugging in x 0? It made the sine term disappear. What about plugging in makes the cosine term disappear? Try power 2. By the way, the suggestion to plug in 1 will work, but I've got to bring the size of charcoal briquette. I'd rather not do the computation set, right? So if I plug in power 2, now the cosine term is dead, right? So let me kind of collect what I've got over here. C1 plus C2 is 0. What's something else sagacious that I might plug in? How about minus power 2, right? A power 2, a positive choice tip, right? I think somebody said pi. Let's do that. Minus power 2 will work as well. How about pi? I get C1, that's a 0 again, minus C3, 0. you know, now it's funny because now that I've got these three equations, I need to convince myself that the only way to do this is C1, C2, and C3 all have to be zero, right? So I'm gonna do a little linear algebra to solve my linear algebra. This is a homogeneous equation, right? And the matrix should be 1, 0, 1, 1, 1, 0, 1, 0, minus. Everybody agree with that? So let's row reduce this. 1, 0, 1, multiply by -1 and add. And again, multiply by -1 and add. Everybody agree with that? How many solutions are there to this homogeneous system? Only the trivial one. Everybody agree? Because this has hits everywhere, right? And so that's what we need. So this set is linear and any questions? Yes.
We have something like a sin x and a cosine x function. And we know that those two functions are always bounded inputs. Wouldn't that always mean there's a finite number that can be? Like
What's that?
we add a finite value to anything inside a cosine function because they're bounded inputs. I mean, there's always a number that can be taken. We assume that.
Well, so if I give you this equation for some choices of C1, C2, and C3, if these numbers are right, you might be able to find a particular value of X that makes it zero. But for linear independence, this has to work for every value of X, right? So when I ask if these are linearly independent, for what I'm asking is, look at this equation, C1 times this, C2 times this, C3 times this. Is this zero, not just for some X, but for every possible value of X? And that's the difference. That's why it turns out. I mean, can you solve this? Well, yeah. So for example, if I had this to be 1, this to be 1, and this to be 0, right? I could plug in X equals minus pi over 2 and get 0, but that's only for one particular value. It has to work for every value of X. Yes.
So if we're asked to solve this on a quiz or something, is this how we go about solving it, or is there a better way to show it's linearly independent?
This particular one, probably for this problem, I think that probably is. I did more steps than I would require you to do, but this is probably the best way to solve this problem. Let me give you a contrasting example. Maybe this will help. Well, how linearly independent set? No, it's not. Why not? What's a big giveaway?
Sounds perfect.
For every single value of X, that's true. Right? So you get the equation. So for my choices, 1, -1, -1, this is 0 for every stinking value of X. So this is actually a linearly dependent set. Some of you, especially if you're electrical engineers, will probably at some point see Fourier series. And what that does is that depends on bases of large vector spaces. Looks like this, right? How many of you have seen waves in your labs, stuff like this, right? Sometimes you write functions in terms of sines and cosines. This is very important in the development of that and writing things this way. Okay. Any questions? Okay, so let me give you a definition here. definition. Let B be a vector space. S, a subspace B, maybe even the whole vector space B. And fancy B, this collection of vectors. Collection of vectors. All in out. All these B's are in the subspace S. B is a basis for S if number one, B is linearly independent. So anything that I call a basis has to consist of a linearly independent set. And two, anybody want to guess what the next one is? When we talk about basings for a subspace, when you're talking about subspaces far in, what two things do you need? You need to be linearly independent. What else? Span. Yeah, it needs to span. Right. That's the span. So there's two things going on here. Number one, the set of vectors is linearly independent. So in a certain sense, that means it's as small as possible. And number two, everything in S, everything that lives in the subspace is a linear combination of these vectors. All right. So a linear, by the way, a basis is not unique. If I walk up to you on the street and give you a vector space, it's usually got many, many bases. What is true is if this subspace S has n vectors in its basis, then every basis will have exactly n vectors. We say that dimension is n. That's the number of vectors in not just this basis, but any basis. Okay. Let me give you an example. Here's the, these are all polynomials of degree n or less. Anybody give you a basis? Anybody think of a linearly independent set that spans this so that everything's a linear combination from that set and it's linearly independent? What's the easiest basis that you can think of? Right, how about just the powers of x? You should check if this is linearly independent. It's very much the same as what we did before. And the fact that it spans it is pretty obvious because anything in PM looks like this. So it's A0 times this, plus A1 times this, plus A2 times this, all the way up to A. Right, okay with it? What's the dimension? What's the dimension? Oh, tricky teacher. It's not n. N plus one. Right, you start counting at the 0 power, but see how evil are you? Here's another basis. You should verify that this works. If you remember last time, we looked at a particular example of this, and we had the linear transformation of taking a derivative right in this matrix. You can also reinterpret this in terms of the matrix. This is called the standard basis. And by the way, if you rewrite this, if you think of this as E1, E2, E3 up to En plus 1, you will, and you write that as a matrix, you'll get a diagonal matrix. If you think of this, what are you supposed to matrix will look like here? It won't be diagonal, but it'll be almost as nice. Yeah, it'll be triangle. Yeah. Okay. Questions so far? Okay. Here's some other examples. Here's another vector space that is a little off the beaten path, but it's not too different from what you're used to. All the 2 by 2 matrices, but I'm sorry, 2 by 3 matrices, 2 rows, 3 columns. A1, B2, A3, B1, B2, B3. I claim that this is a bona fide vector space. Question: what happens when you add two 2 by 3 matrices? What do you get? You get another 2 by 3 matrix. Everybody agree with that? You add them up. What happens if you multiply that thing by some constant? What do you get? Another 2 by 3 matrix. This is a bona fide vector space. Add 2. Now I'm calling this matrix effect. Add 2 vectors, 2 by 3 matrices. I get them in 2 by 3 matrices. Multiply by constant. Get 2 by 3 matrices. Anybody guess what a sagacious basis for this might be? What's a good basis? By the way, anybody want to guess what the dimension of this is? 3. I want to go 6. What makes you think 6? There. 2 by 3. Okay, so does that inspire? So since you think it's 6-dimensional, does that inspire a choice for a basis?
A1 equals 0 equals 1, everything else is 0. A2.
There you go. Notice that everything is a linear combination. My random matrix over there, A1 times this, plus A2 times this, plus A3 times this, plus B1 times this, B2, B3, right? And it's actually not too difficult to verify that these things are, that this is linearly independent. I can almost do this. So suppose that I have a linear combination of this, A1 times this, A2 times this, A3, B1, B2, B3. When I add it up, it's going to look like this. Now set it equal to the 0 matrix, and what has to happen? Every one of the entries has to be 0. So it's easy to check if that's linearly independent. Any questions? So what would the dimension of, let's generalize this. What if I had an M by N matrix, right? And I thought of that as vector space. So I looked at all the M by N matrices. What do you suppose the dimension of that would be? M times N, exactly. Good. Okay. Here is a theorem. This is yeah. So I've got two big theorems, and I want to kind of go through another kind of column space sort of thing. Where are we? Here. Okay, theorem. This is called expanding set. Let the vector and S is a collection of vectors. No. Say S is the span. By the way, I didn't say this, but these vector space, each of the vectors VI's and T. So I have some vector space, some maybe huge vector space, and I just take a collection of vectors and I look at what they span. I did this in a couple of examples, right? I took the vector space of all continuous functions, and I took three vectors, one, sine x, and cosine x. Those are three continuous functions. I looked at what they span, right? Every linear combination of one, sine x, and cosine. That's what I'm doing here. Now, let me ask you this. V1 up to Vn. Is that a basis necessarily of S? What do I know and what do I don't know about this with regard to that being a basis? Well, this set certainly spans S, right? If I agree with that. So that's one of the things I need for a basis, right? So I've got that. So V1 up to Vn could be a basis because it spans all S. What might make it fail be a basis?
You can say in all of X plus vectors.
Okay, right. Actually, you're a step ahead of me, but that's right. If it's linearly dependent, right, it won't be a basis. And what does it mean to be linearly dependent? It means one of those vectors can be written as a combination of the others. So here's what I hope. I hope I might look at that and say, well, this spans space all right, but yeah, some of them are linearly dependent. Maybe I can go through and cherry pick, just pluck some of these vectors out until I'm down to a basis. And the answer is yes, you can always do that. So let me be precise here. If one of the vectors we'll say the ith one, the I, is a linear combination of the others. Then you can throw it out because it's a linear combination of the others. You don't really need it in the span. Then the collection of vectors V1, Vi minus 1, Vi plus 1, Vn still spans S. So in other words, if you look at your collection of vectors and you find, hey, look, this vector Vi can be written as a linear combination of the other vectors, you can punt it. You can kick Vi out of a little club And whatever's left over still spans it. And B, if S is not equal to the zero vector, so of course, one thing that could have happened if all those vectors had been the zero vector or something like this. If it's not the zero vector, then some subset of V1, V2 up to Vn is a basis. Okay, so what is this theorem saying? Well, this theorem is saying, look at this collection of vectors, right? This collection of vectors spans some space S, right? Now, if there is a vector in there that is a linear combination of the others, then I can just throw it out. And whatever's left over still spans S. Right? Now, if that's a linearly independent set, when I throw out the row thing, then I've got a basis, right? But if not, that means that one of the other vectors is a linear combination of what's left over, right? So I kick it out, and I kick it out, and I just keep continuing the process until I get to a basis. Now, that's a little bit fast and loose, so let me make this a little bit more precise. Y is a suppose VI is a linear combination is A1 B1 plus AI minus 1 BI minus 1 plus AI plus 1 BI plus 1 plus A. Suppose that this guy can be written in some linear combination. And let B be in the span of S. Well, what does that mean? That means B is equal to C1 D1 plus CI minus 1 DI minus 1 plus CI BI plus CI plus 1 DI plus 1 plus CN. So what does it mean to be in the span of S? It means it can be written as a linear combination of all things, right? Well, what do we know about VI? It's this. Everybody agree with me? So I can take a crowbar and jam this down here next to CI. And what do I get? I get a big fat mess. But I'm not even going to try to clean it up that much. What I now get is B is C1 D1 plus CI minus 1 DI minus 1 plus, well, now I've got CI times all this garbage, right? That's Get City, but I will persevere. CI A1 D1 plus CI AI minus 1 DI minus 1 plus CI AI plus 1 DI plus 1 plus CI AN DN plus whatever's next, CI plus 1 DI plus 1 plus CN. Oh, God, what a mess. But here's the deal. Now B is a linear combination of all these V's, and you never see an I appearing, do you? Right? Because there's no I here, it's missing. There's no I here, it's missing, and there's no I here. So now B is in of B1, BI minus 1, BI plus 1, and then we'll expand it with one less. Fine. And that's exactly the same here. And I'm going to talk you through the last bit, and the last bit is merely this. Start with, and we'll assume that S is not 0. So at least one of these vectors is not 0, right? Let S be the span of this. If this is already linearly independent, then I have a linearly independent set that spans S, and I'm done, right? If it's linearly dependent, that means that one of these vectors is a linear combination of the other, right? So I toss this out and use this part. Throw out one vector, and now I've got one less vector in here, and it still spans. If this is linearly independent, then you're done. If it's not linearly independent, do this again. Throw out the linearly dependent one, and now you span it by something even smaller. Keep going until none of these is a linear combination of the others, right? And then what you have is a linearly independent set that spans. Everybody agree? And what happens if you get all the way down to one vector? Well, if you get all the way down to one vector, if you throw everything out except V1, since this is not 0, this means that V1 is a single vector that's not the 0 vector, so it's linearly independent, and it's base and it's the basis of it. So the process must terminate. Yes, sir.
Okay, so this might not be thinking about it right, but if you were to have all those V's inside of a matrix, and are you technically just throwing out the non-pivot columns?
Oh, okay. So if you think of this in terms of, yeah, so if you think of this as a column space, so you're harkening back to the days of RN and put it in the matrix, right? Which we're not done doing, by the way. So if you take all these V's and you put it in a matrix, right? He's right. Well, one process that will do that is you can row reduce the matrix and know which columns are the pivot columns. And what you're doing is throwing out the non-pivot columns, right? That's what you're doing in the old days. Okay. All right. Let me give you one last theorem, and this is actually a deep theorem, and it's true for more than just finite dimensional vector spaces. And I want to, you guys should know this theorem, but here, so I'll give it to you. Theorem. Let B be a vector space or a subspace. Number one, if V1, well, is a linearly set subset of then B1, B2, Bn is contained in a basis. Okay, this is actually kind of a deep theorem. So what it means is, if you have like a 7-dimensional vector space, if you find any two linearly independent vectors, that is, any two vectors that aren't on the same line, right? You can take those two vectors and find another 5 vectors to add to it to make it a basis for your vector space. Any linearly independent set is a seed, right? If it's a basis already, good for you. If not, you can just start tacking on new vectors until you reach a basis. This can always be done. Yes.
How would you tack on more vectors? Like, just make it up or?
That's a good question. So how do you make these? For right now, you just kind of make it up, but we're going to get to some things later where I can actually give you an algorithmic process in certain vector spaces to do this, right? But yeah, what you'd have to do is you'd have to find something. So what you can do is if these don't span all of the vector space, then it spans a subspace. Agreed? So if this doesn't span all of V, if it's not a basis, then when you look at the span of this is a subset of V, and it's not all of it, right? Find something in V that's not in the span of this, and that'll be your next element. If that's a basis, fine. If not, there'll be something left over, and you can continue this process. Now, this is very intuitive, and one of the reasons that this works, this actually works for infinite sets as well, as a matter of fact. So this is a deep theorem. And number two, if let's see. If V1, V2, Vn spans, then this set contains bases. And that's essentially the content of this previous result right here. Okay. Any questions on that? So if you've got a spanning set, you can always collapse it to a basis. If you've got a linearly independent set, you can always grow it to a basis. So spanning set, you got to prune maybe. Linearly independent set, the seed's got to grow. Let me give you an example. I wanted to do one like this. And this is just, so this is time for you guys to kick back and relax because this is similar to what I did before, but I want to demonstrate something here. This will reduce fast. I want to find a basis for null A and column A. This is what is null A? In this case, it's solutions to AX equals 0. But in general, what null A is it's also the kernel of the linear transformation of the set of things under a linear transformation go to 0. So let's roll with this matrix here. Let's take the first. Take this 1 to take this out, minus 1 and add. 4 minus 4. And then times minus 2 and add. 0. 5, 5, minus 5. Huh. That worked out nicely, didn't it? So this was, or this is, 1 minus 3, 0, 5, 0, 1, 1 minus 1, 0, 0, 0. Right? Because these both reduce to the same. Everybody cool with it? One more step so I don't confuse my pea-sized brain. 0, 0, 0, 0, 0, 1, 1 minus 1. Multiply that by 3 and add. 3, 2, right? Okay. Now, this is a good example of having to be careful about column space. What's the basis for the column space? should be what corresponds to the pivot columns here. You have to use the original matrix. And this example is -3, 1 minus. Right, everybody okay with that? Tell me why, if you use pivot columns in the reduced matrix, it's wrong. This can't be a basis for the column space, because what is true about the span of this? What's true about the third coordinate? It always must be what? 0. But isn't it clear that the column space certainly contains third coordinates that are not 0? Right? So if you use these first two in this matrix, you're definitely wrong. Right? So that's why you gotta go back to your roots here. It's time to go, so let me give you the null space. Let's see if you can figure this out. This is what I got. I got -3, 1.0, and -2, 1.01. So see if you control that out. I guess my answer makes sense because the dimension of my column space, I'm going to switch both two, and that's a new column. Okay, questions? All right, you all have a good one, and substitute will be here Friday, but have a good fall break.